Righto, welcome back, sports fans. Back to another exciting edition, mathematics, in confinement, in quarantine. Right, we're going to have a look at solids of revolution. This is an extension. I've done a little review right at the start. We've got to get a little bit back to basics here. When we have a look at hair end of the curve, we happily dive into integration and we know all the little numbers go here and there, and we're getting pretty good at it. Let's just go back right to the start and review what's going on with this calculus business. All right, so we have some curve, some function. Let's doing some stuff here. We want to find the area under this curve through here between 0 and 10, some arbitrary number. All right, so this is what we'd write down. We'd have some function here, x cubed plus 5x squared, some bloody thing. Do our integration, do all our stuff, happy days. We're getting on top of that. All right, if we review very carefully these little dx patches, we have here this little strip of dx. Remember right at the start when we looked at shapes and how we could squeeze them underneath. Maybe this is a rectangle and a trapezium, you know, Simpson's rule. You haven't done Simpson. Trapezoidal rule. That can be pretty accurate, but it's still not as accurate as using calculus. So let's quickly review this little rectangle. If we pull it down here, how wide is it? It is dx wide. It's a thin paper strip, thin of stuff. Area of a rectangle. So area of a rectangle is simply length times breadth, height times width, whatever it is. How wide is it? It's dx wide. How tall is it? It's y tall. It goes up to the y-axis. So y also equals fx, so we can change the y's into terms of x's. So writing all that down using calculus, we can say I want to add up all the rectangles. That's what this is saying. This is what this calculus bit's saying. The sum, that's the sneaky sort of squished out s. I want you to add up all the bits, all the little rectangles between 0 and 10, and we do our calculus stuff and we're good to go. We just put it all together. But please don't forget that is a little thin strip. It's a dx strip wide, and the calculus says to add up all those and come up with the area under the curve. Right, if we move into volume, it's the same principle. It looks a bit more messy, but it's the same principle applied. If we have some function, I've just made up a function here, and we spin it around an axis, it could be spun around an x-axis, it could be spun around a y-axis. If we spun it this way, it sort of makes some sort of bizarre coney sort of shape. This one sort of makes a crazy looking bowl, sort of half drawn right there. I don't know how good that is. Right, so I've spun it around. But again, I have this little thin strip, so if I rolled it down here and spun it around, it'd make a coin, if you like, sort of a crazy coin. Now, calculus says, I want you to add up all those little thin paper thin strip coins, add them all up, and put it all together. Well, that's what we're doing over here. Now, recall, please, the volume of a cylinder. I want the face, pi r squared, and times it by the depth. We call it the height, but it's really the depth of it. So putting all that together, I've got pi r squared times the dx bit. So pi r squared, and remember my height of my radius of my coin, or this crazy coin here, is actually y. So we might need to change that in a moment in terms of x's, because we're talking dxy. All right, so going further again, I've spun my function around, got some crazy shape. Remember that this strip also produces a small coin shape here. It is dx wide, its radius is y. So putting all that together, I can't show that. I end up with a formula a bit like that. All right, the best way to probably do this is actually have a look at a real life question. So we'll just get out of that. And here's one here. I'll send you all these questions. This was in a HSC back in 2017. I don't think I've ever seen a HSC that hasn't included one of these questions in that. They do vary in difficulty, of course. Here's a function, root 16 minus 4x squared. It's all this crazy function here. Diagram shows the region bounded by. Does that scroll up? No. And you're asked to spin it around the x-axis and forms a solid, sort of like a crazy sort of pill sort of shape. But we're going to use the same thing. We've talked about a dx strip wide. We've got a coin down the bottom there. It is dx wide. Sorry about that, just ignore that for the minute. Its radius is a height of y. So V, the volume of this one single coin is pi r squared h. That's one of them. I'm going to use a bit of calculus, integral calculus, to add up all those little strips all the way. Now I've broken it up rather than going from add up all the coins all through here. I've just noticed that, well, it's symmetrical, so I'm just going to add up from there to there and double it. That's probably the easiest way to do it. Symmetry will help with that. All right, so paying attention here, please excuse a mess all over the shop and some of the bad writing. So I'm going to add up all my little strips. Oh, paying attention to, of course, that pi is a constant, so it can come out the front here. I'm adding up between 0 and 2. You could do -2 to 2, but I'm just symmetry-wise. I've set it all. Now, the radius squared, that's r squared. Well, that squared removes that square root sign, so that's a real bonus to it. So there's my radius, and I want the radius squared, so that removes that square root. So there's my function I'm going to have to integrate. So it's going to be the constant term at the front, which is that pi r squared. There's the pi at the front. The radius squared was the y squared, but the y squared thing can be turned into 16 minus 4x squared. So that's a relatively simple integral step. And I have to double it because I'm going from 0 to 2, not from -2 to 2. So I'm going to also put that constant term, that 2 out the front. So I've got now 2 pi out the front. I've integrated the 16x, integrated the 4x squared, 4x cubed. I'm adding up between 0 and 2. That just becomes a really simple integration. Putting all it together carefully, hopefully you've got it all right. 128 pi. And they'll normally ask, if you haven't already seen it, a lot of exact values. Find the exact volume. All right, so it has to be exact. So don't bother trying to work that in the calculator. It's a volume question. It's not a arithmetic question. All right, now I'm not sure if you've seen it already, but you can spin it on the y-axis. All right, so that's this crazy shape. But now everything, how wide is that? Now that's going to be a strip of dy wide. All right, not dx, we're not going this way, we're going this way. Setting up the question, find the point of intersection here. All right, now that's got nothing to do with calculus yet. Point of intersection is where those two curves are the same, so they're the same there. Solving. I get x equals -2 or 2. That makes sense on my diagram. Yes, it does. Point of intersection, and also don't forget it says the point of intersection, so I have an x and a y. Done all that stuff there. All right, now to do the volume. Now I'm going to spin it this way. Another coin, it is dy. It's still pi r squared on top. Pi r squared, what's my radius? My radius this time is going out to x. All right, a few blues there, don't know what's going on there. All right, so there's my radius. X is given by, well, that's my original formula. I don't want x by itself, and remembering that it's going to be the radius squared, so I want x squared by itself. So there's x squared by itself. And there's my volume, V1, must be the top bit and the bottom bit. All right, so I'm going to, that's what I was trying to do before. So to add this up, I'm going to do the volume of the top function here all the way down to that point of intersection. So 12 down to this point here, and then the bottom bowl. So the top bowl that's sitting at the top, and that's the volume 1 and volume 2. All right, so there's the top one, as I've said. And notice that I'm going between 12 and 4, and assuming the next one will be between 4 and 0. So there's the integral put together there. 6y, that's that top function, integrated. And there's volume 2, which is the bowl on the bottom between 4 and 0. And integrated. So adding up those two amounts, 24 pi. Now there are solutions on the worksheet, which I'll include. All right, adios.